There we go. All right. I think I'm going to make a video on this as well. But because your homework is online, I'm often afraid that you're doing work like scrap paper or maybe just sort of on your calculator and not writing things down. I think a better way is to maybe keep a notebook or keep certain pages where you're doing your homework and can go back to them or refer to those.
Turn it into a PDF too.
Yes, I will turn this into a PDF. I plan on making something for you that you can fill in if that's how you would like to do that. So sort of the thing that I think about when I'm working on problems, a lot of what you're going to do this semester is problem solving. Writing out the problem text could be shorthand, just briefly what is the problem, what is the goal, like what are you looking for, what's the problem asking for, what things do you know already, so what parameters are given in the problem, and just sort of have those at the top of the page, or top of the portion of paper that you're working on. And work out the problem and be sure to write out the assumptions that you're making. Often we are going to make several assumptions while we're working on problems, even with our concentration unit conversion problems, and more so during the rest of the semester. And then I think the really big things that are important are writing out what's confusing, so that when you go back to it, you can just look at that section and say, oh, I remember I have to do this, or I got stuck here last time, and then write down how to avoid getting stuck. And then an extra sort of step there, and this goes into our metacognition, is what's another problem that is similar but related? So you only change maybe one parameter, maybe we're asking for a different, to solve for a different thing in an equation, something like that. Okay, so just sort of thinking about how exam writers are writing exams, that's that last box there. Okay? Okay, so with that, let's work on some problems. So I have a couple examples here from unit conversions with concentration. So the first one is, what is the mass percent of glucose in a solution that is made by dissolving 5.6 grams of glucose in 25.2 grams of water? So again, we're looking for mass percent. So that's what we want. If we go back to our units, remember that mass okay. And what do we know in the problem? We know the mass of the solute, the 5.67 grams of glucose, and we know the mass of the water, that's the solvent. Okay. So how do we find the mass of the solution? We add up the mass of the solute, which is the glucose, and the mass of the solvent. Okay? And so, I'm just going to write this into our mass percent equation, because that's what we're looking for. We're trying to find mass percent, right? So we're going to have 5.67 grams of the glucose solute over 5.67 grams of the solute plus the 25.2 grams of water. So again, mass of solution, SOLN, equals mass of solute plus mass of solvent. and adding up the numbers in the denominator, dividing the numerator by the denominator, should get 18, times 100, sorry, I always forget that, should get 18.4%. That one's relatively straightforward. Does anyone have a question? Where's an easy mistake? Yeah. Yeah, just putting it over the solvent, totally easy mistake to make. All right, but it's massive solution. It's got to be solute plus solvent. Good. Okay, let's look at a different one. This one, we're going to up the difficulty here a little bit. So here we're saying how many grams of water are needed to make 1 kilogram of a solution containing 5.5 mass percent sodium chloride. Okay, so what do we want? We want to find grams of water in 5.5 mass percent NaCl. That has a mass of the solution of 1 kilogram. SOLN. Okay. That's our goal. And what we know is the mass of the solution is equal to 1.00 kilograms. And again, this is mass of solute plus mass of solvent. We also know the mass percent, right? So it's 5.5 mass percent sodium chloride. So we go back to our mass percent equation. Mass percent equals, let's do mass of NaCl over the mass of solution times 100. Okay. So now we can start plugging some values into our equation here. We know our mass percent, that's 5.50. We know the mass of the solution, that's 1 kilogram. So we can solve for the mass of the sodium chloride. So we're going to do that, divide both sides by 100, multiply both sides by 1 kilogram, and we will end up with, in kilograms, 0.0550 kilograms of NaCl. Everyone okay with that? Are we done? No. Right? This would be an easy place to just stop and say, oh, I solved for a thing. But it's not what the question asks. Again, we want to know the mass of the water. And it said grams. Okay. We can find it in kilograms, and then we can, for today, stop there, I guess. So we know, now we know our mass of the solute, right? So this is mass of solute. Sodium chloride is our solute. And now we can actually use this equation here, where our mass of solution is equal to 1 kilogram, which is equal to mass of solute plus mass of solvent. So let's plug that back into, plug our mass of the solute into that equation. So we have 1 kilogram is equal to 0.0550 kilograms of sodium chloride plus mass of solvent. and solve for the mass of solvent. We get 0.945 kilograms of water, right? The conversion from kilograms to grams, and this one I want you to kind of become familiar with, so it's more automatic. So 1 kilogram is 1,000 grams, and so this is 945 grams of water. Questions on that? Yeah.
Ever do that for like an assignment or a test? Do we have to do it that way?
There are probably other ways to solve it. I mean, do you have an approach that you're thinking of?
Yeah, I just took the 1 kilogram
Uh-huh.
and I made that 1,000 grams. Then I did 1,000 grams times 0.055 equals 55 grams, and then 1,000 minus 55.
Yeah.
That's 945.
Yeah, that'll get you there. Yep. Yeah, so there are other ways to do these problems. Practice them, make sure you're getting right answers, right? If it works for you, if it makes more sense than doing what I've done, that's fine. I think with equations, so I like plugging values into equations. That's why I choose to do these this way. Let's do one more. This one is a bit more tricky. I'm going to let you guys, let you all work on this for a few minutes on your own, and then we'll work on it together. I'll read it out loud here. We have a 0.537 molal solution of sodium hydroxide with a density of 1.13 grams per milliliter. What is the molar concentration of the solution? So you're going from molality to molarity. Yeah, feel free to work with your neighbors, totally fine. Want to do that? So again, there's probably going to be multiple ways to solve this problem, but I'm going to show you the way that I work through this. So again, our goal is to find the molarity of the sodium hydroxide solution. So we want to find moles of sodium hydroxide per liter of solution. Okay, so with molarity, I always like to remind myself that that denominator is liters of solution, okay? Not just liters of solvent, liters of solution. Okay, and so what we know is the molality, which is moles of sodium hydroxide per kilogram of solvent. In this case, that's water. Okay. We're also given the density. Okay, I'm about to say something really important. Density, your eyes. Density, okay, density is for a solution, okay, not just for a solvent, it's for the solution. So in this case, it's 1.13 grams of solution per milliliter of solution. Okay, and I'm leaving the solution written there, okay, because that unit is going to be really important in solving these problems. Right? So when you see density, remember it's for the solution, it's grams of solution per liter of solution. You can maybe see where we're going to go. We're going to have volume of solution here. We're going to need volume of solution. Okay? That's why it's key to remember that. All right. Any questions? Did anyone make any assumptions for this problem? Okay. I'm going to make an assumption. I don't know how you did it without, but that's fine. We can talk about that later. I'm going to assume that I have 1 kilogram of solvent. Why am I doing that? If I assume I have 1 kilogram of solvent, if we look at what we know our molality. If we assume 1 kilogram of solvent, we can figure out how many moles are in 1 kilogram. And when we find molarity, the molarity is the same no matter how much of that solution you have, right? So we could assume we have 100 kilograms. We could assume any number, right? It's just that in order to figure out moles, this is one way to do it. And it works efficiently to do 1 kilogram. Math is nice that way, right? Okay. So if we assume 1 kilogram of solvent, so we can calculate the moles of sodium hydroxide. So we were starting with what? 0.3537 moles of sodium hydroxide per kilogram of solvent. Assume 1 kilogram. I'm going to put my arrow here to show that's where I'm doing that. And so we end up with 0.537 moles of sodium hydroxide. Okay. That assumption allows us to figure out then the volume as well, okay? Because now we have a mass for that solvent. But again, density is mass of solution per volume of solution. So we need to know next the mass of the sodium hydroxide that's present in 1 kilogram. That's present in this solution when we assume we have 1 kilogram. So let me write this way. So we need to find the volume of the solution, right? Eventually, right? We need in our denominator liters of solution. Okay? So we need to find the volume. And we can use the density. So we have 1.13 grams solution per milliliter of solution. All right? But we need the mass of the solution in order to find the volume. We've already assumed 1 kilogram of solvent. So we know the mass of that. So now we just need the mass of the sodium hydroxide. Right. Everyone following that part? It's a little tricky. This is where it's easy to get confused. So we're going to take our moles of sodium hydroxide. What are we going to use to find mass? Molar mass. So we have 0.537 moles of NaOH. We use the molar mass, which happens to be 40 grams of sodium hydroxide per mole. You'll find that I use dimensional analysis for everything. It is my favorite form of math. Okay? And moles cancel, and we end up with 21.48 grams of NaOH. Okay, that's in grams. Our solvent's in kilograms. Let's put everything in grams. So 1 kilogram is 1,000 grams. So the mass of the solution is going to be 1,000 grams plus the 21.48 grams of sodium hydroxide, which is 1021.48 grams. Before anyone asks, don't come at me with sig figs. Okay? I hate sig figs. As an analytical chemist, you would think, I would like sig figs. This is about precision. But the way we teach it in analytical is so much easier than what you have to learn, and it's so irritating to me. When we do our math like this, I probably won't bother with sig figs until we get to the very end, if at all. Not to say that you shouldn't know them and that you won't know them for lab. You won't need to know them for lab. You will. It's just another battle I like to fight. Okay, so now we have massive solution in grams, so we can use our density to get the volume of the solution. So 1021.48 grams of solution, remember that, times the, divided by the 1.13 grams of solution per milliliter of solution, which gives me 903.96 milliliters of solution, or 0.90396 liters of solution. There's 1,000 milliliters in 1 liter. Okay, that's where that's coming from. Okay. So now, wow, we scroll all the way up here. We've got our moles of sodium hydroxide, 0.537. We've got our volume, 0.9039, etc. And so we can finally find the molarity. And we end up with 0.594 moles per liter. Capital M for molarity, moles per liter. Questions on that one? Yeah. How did I know it was talking about molarity? I believe it, let's see, so we go back to the question, make sure we answered it. So we wanted to know the molar concentration of the solution. The molality versus the molarity? Yeah, so if we look at our equations here, this is molarity. Our goal is moles per liter of solution, moles of solute per liter of solution. Molality is usually lowercase cursive m, and it's moles of moles of solute per kilogram of solvent. We are going to use molality a lot when we talk about colligative properties, which is the next section. We'll start here shortly. And because those are going to be dependent on, well, they're going to be dependent on molality. So Know those units. Apart from colligative properties, I don't think molality is used very much elsewhere. So, there's that. Other questions? Yeah,
You go back to the bottom.
back to the bottom, yep. Anything else? Yeah.
What's the reason that dividing by 1.13 wouldn't work? Because if it's 1.13 grams per milliliter, shouldn't it be 1.13 kilograms per liter?
Oh,
And then dividing by that, but then dividing by that should give us the right units, but it's giving different units.
wait, did I miss that by math? Is that what you're saying?
No, I'm saying.
It's possible.
Something's weird.
Totally possible.
No problem.
Did anyone check while we were working? Okay. Yeah, feel free. It's always possible that I made a mistake, so. Okay. But yeah, so the question was, in terms of density, wouldn't it be the same, instead of grams per milliliter of solution, couldn't it be kilograms per liter? And yes, as long as you're treating the numerator and the denominator the same way, and that way we're multiplying by 1,000, then yes, that's the same sort of thing.
Wait, what was the original? The original molality?
0.537? All right. There is another set of slides on Carmen, so I'm going to switch